So this next section is my favorite section in our whole course. We're going to be learning how to prove trigonometric identities. And I love it because it's so creative and really gets you to think outside the box. Really learning how to prove trigonometric identities was the moment when I fell in love with math when I was in grade 11. So I hope you feel the same way. So far what we've been doing is trigonometric equations. An equation is something that's intended to be solved for theta. So if you had an equation like this, sine theta is equal to a half, right? You might do this with your unit circle, or maybe you do this. You'd say theta 1 is the inverse sine of a half, right? And your calculator would spit out 30 degrees there for theta 1. And then you'd use your related angle to get theta 2. Be 180 minus the theta 1, or 180 minus 30, so that's 150. And that would give you your two solutions between 0 and 360 for theta, right? So that's the idea of an equation, is you're just trying to solve for what theta is. What's cool about a trigonometric identity is that it's not just true for whatever the solution is, whatever that one or two answers for theta is. It's true for every possible value of theta. So there's not one theta to solve for, or even two thetas to solve for. There's an infinite number of thetas. It's a relationship that's always true. So this is an example of one. If you do tan of an angle, so you can pick any angle you like whatever your favorite number is. I like the number 23. So if I do tan of 23, try typing that into your calculator, see what number you get. And then also try doing this. Try doing sine of 23 divided by cos of 23. What you'll notice is that those things are equal to each other. And that will be true no matter what angle you pick in here. You didn't have to pick 23 degrees. You could pick your favorite number. It could be a negative number. It could be bigger than 360. It will always be true. So a trigonometric identity is true for all values of theta, not just sort of something you can solve for one or two values of theta. So why do we prove these? Why do we worry about them? One is that they're super useful. So when you get into complicated equations in physics and biology and engineering or in math, we need to simplify those equations down. And if we have some trigonometric identities, it lets us simplify things. So say the one that we just saw there, tan theta equals sine theta over cos theta. That means if you're solving something more complicated and you see a sine theta over cos theta somewhere, you can replace it with just a tan theta, which is simpler. But we'll get into even more interesting trigonometric identities than that that can be simplified even further. So that's one reason. They're just practical, they're useful. But a bigger reason, and this is why I fell in love with trig identities, is it really makes you think creatively. There's not like a simple process to solving them or proving them. There's not sort of a formula that you're plugging things into and following the same process every time. It's different every time, which really gets you to think outside the box. And it means that it's the best feeling ever when you actually get to prove a trig identity and it works. It takes longer, I find, than other math problems. They're harder. You work at them more, but when you get them, it feels so, so good. So I hope that you have the same excitement and joy when you prove trig identities in this unit too. I hope you find them fun. All right, so in order to prove trig identities, we need a toolbox of sort of fundamental identities that we're going to use to prove new identities. So one is the quotient identity, and that's the one I just showed you, that tan of theta is equal to sine of theta divided by cos of theta. And actually, we've talked about this one before. It comes from your unit circle. If I draw, say, some angle theta here on my unit circle, right, and then I could draw from that little triangle. Right, this side here is the y value, and we know that y is sine theta. And then this side here of my triangle, it's a right angle triangle. That's cos theta. It's the x value of this point on my unit circle. And the hypotenuse, we remember, is 1 there. If I write down what tan of theta is, just using SOHCAHTOA, right? SOHCAHTOA. We use the TOA part of that, right? Tan of theta would be the opposite divided by the adjacent, right? Well, here, the opposite side is that purple side, that's the sine theta. And the adjacent side is the blue side there, well, that's cos theta. And that right there actually is the quotient identity. So this means this is true for every single value of theta, that sine of any angle divided by cos of an angle is equal to tan of that same angle. So that is a fundamental identity that we're going to use to prove more complicated and more interesting identities. There's another one that we'll use a lot, and that's the Pythagorean identity. So this one also comes from the unit circle. So draw my little unit circle here, and you can draw any old angle on your unit circle. So there's theta. And draw your triangle again. So the x part here is cos of theta, and the y coordinate here is sine of theta, and that's a right angle triangle in there. And the hypotenuse is still 1. Well, this is called the Pythagorean identity for a reason. If we use the Pythagoras' theorem on this triangle, I would do sine squared theta, right? This side squared, plus the other side squared, cos squared, would equal the hypotenuse squared, right? So this is literally Pythagoras' theorem. A squared plus b squared equals c squared, where a and b are the two sides right beside the right angle, and c is the hypotenuse. You can simplify this a little bit. 1 squared is just 1, and I get sine squared theta plus cos squared theta just equals 1. And that right there is the Pythagorean identity. So whenever we see a sine squared theta plus a cos squared theta, we can replace it with the number 1, which is beautiful. This feels like almost too good to be true, so you should check and see if it actually works. So pick any value of theta. I'm going to pick some random number. Let's see, maybe I'll pick 237. So do sine squared of 237 plus cos squared of 237. Plug that into your calculator and see what you get. You will get 1. You can pick any angle you want in there, and you will still get 1. Because an identity is true for every single angle theta. So try your own angle, pick anything so that you know that 237 is not just a magical number that I picked because it works out so beautifully. Sine squared of any number plus cos squared of any number will equal 1. By the way, just how you type that into your calculator, what you have to type in will look more like this. It'll be like sine of 237, to put brackets around all of that and then square it. It's kind of awkward, but that's sort of how you have to type this in. And then cos of 237 and all squared, and that will give you 1. So that's what this means here. Sine squared means that you're taking sine of 237 and squaring that thing. That's what that notation there means. All right, the last thing in your toolbox are actually just some definitions. So we've already learned these. These are your reciprocal trig functions. The cosecant of theta is 1 over sine theta. The secant of theta is 1 over cos. The cotangent of theta is 1 over tan theta. So these ones are just definitions, and we'll use them. So if you see a cosecant, you can replace it with a 1 over sine, or vice versa. You could go the other way too. All right, so how do we prove identities? So there's really just 2 parts to the process. Everything else after this is just using your own creativity. So this is what I love about trig identities. It's also what makes them hard, but it's also what makes them really fun. So there's not a lot of process. There's just really 2 things you have to do. The first thing you have to do is separate everything into the left side and the right side. So you'll write down left side equals, and you'll write down what the left side of your equation is. Then put a line down the middle, and you'll write the right side equals, write down whatever the right side is. But those 2 things can never cross. So this is maybe the most common mistake people make in proofs, is that they want to treat them like an equation that you could solve. You know, if you have something like this, like sine theta plus 1 equals 2 sine theta, something like that, well then we would want to move things across the equal sign. We might collect our like terms. Moving things across the equal sign, that's something you do for solving trig equations. You never do that when it comes down to trig proofs. So for trig proofs, we will not be moving anything across an equal sign. We're going to separate the 2 sides, the left side and the right side, and then nothing crosses that equal sign. They're completely separate. So that's maybe the most common mistake people make. Don't make that mistake. Once you've separated it, then you simplify each side. And your goal is to try and make the 2 sides identical to each other. How you simplify them will change every time. What I'm going to show you is a few different tricks and techniques that work really well and that you can try. So you'll sort of look at your proofing, you'll get better and better at seeing, okay, what could I try here what might work to go forward. And today we'll start with some simpler ones, and tomorrow we'll add on some more complicated ones. All right, so here is a proof. So this equation is true for every value of theta. So if you want to check and make sure that's true, you can plug in any angle here on both sides. You'll see that both sides will simplify to the same number. But to actually prove it, that's not enough. So just plugging in a single angle and showing that it equals the same number tells me that it's true for that one angle, but I need to prove that it's true for every angle theta. So to do that, I have to do a formal proof. So for that, what I do is I write down the left side over here. And I write down the right side over here. So I actually separate these into two different things. And I draw a line between them, which tells me nothing can ever cross that equal sign. So that equal sign is just like gone. We're not even writing it anymore. We've written the left side and the right side completely separately. Then you want to work on each side and try and get it to look like the other side. So right now they look completely different from each other. So this is where we need a few sort of common tricks. If you see something that looks like a 1 minus a cos squared theta, or 1 minus sine squared theta, this reminds you of the Pythagorean identity. The Pythagorean, it's close to the Pythagorean identity. The Pythagorean identity, if you remember, is this. So 1 is equal to sine squared theta plus cos squared theta. But if I move the cos squared theta to the other side, I would have this, right? 1 minus cos squared theta equals sine squared theta. And so this is like a version, essentially, of the Pythagorean identity. And you can tell that definitely sine squared theta is simpler than 1 minus cos squared theta, like there's sort of two terms here, there's only one term there. And generally what you're trying to do in a proof is to simplify the sides. Every once in a while you actually want to expand them, go the other way. Your final goal is to make them look the same, but often a good way to make them look the same is to simplify. So if sine squared is simpler than 1 minus cos squared theta, it's a good sign that I should plug in sine squared theta here. So I'll actually replace this entire 1 minus cos squared with a single sine squared. So that means the left side simplifies down to just sine squared theta. Once you've done a major simplification like that, you might want to sort of pause, leave the left side alone, now go over to the right side and see if you can make the right side look like that. Our goal is to turn the right side into the left side, and we have to sort of show each logical step that would get us there. So right now the right side is sine squared times cos squared times tan, or sorry, just sine times cos times tan. So I definitely don't see a Pythagorean identity here, but what I do see is maybe a quotient identity. So if you see a tan theta somewhere, then there's a good sign that you should probably use the quotient identity here. And remember, the quotient identity is this, that tan of theta is equal to sine of theta divided by cos of theta. So let's actually replace the tan theta here with what we know it is, which is sine theta for cos theta. So this is often a good move. If you see a tan theta somewhere, replace it with sine divided by cos. And then see what kind of cleans up here. Well, on the top I have a sine theta times a sine theta here, right? Sine theta times sine theta, and those are both in the numerator, they're both on the top. So that's going to make a sine squared theta. So the right side will have a sine squared theta on top. And then I still have a cos theta here. And now I've combined those sine theta, so that just became a 1 over cos theta. Well, now I can notice that I've got a cos theta on the top and a cos theta on the bottom. So those are going to cancel out, right? Cos theta divided by cos theta, that just makes 1. So those guys are gone, and I'm left with just sine squared theta. So at this moment, you notice that your left side and your right side are equal to each other. That means you've succeeded, you've proved it. So you get to say that you've succeeded. One way that we do it is we just say the left side equals the right side. And sometimes we put a little box there, just sort of like a period, sort of saying we're done, we did it, yay, this feels really good. All right, let's try a slightly harder one. So say we have a 1 over sine squared theta plus 1 over cos squared theta on the left side, and we want to make that equal 1 over sine squared theta cos squared theta. So first move, always separate your left side and your right side. So don't touch anything until the left side and the right side are separate. And my right side over here is 1 over sine squared theta cos squared theta, and draw a line between them because nothing's going to cross that line. Okay, let's look at the left side first. Usually I start by simplifying whatever side looks a little messier than the other. That's usually a good place to start. The left side looks messier because it's got 2 terms, so I feel like that's a good place I should start here. And the special technique that I want to show you here is how to get a common denominator. So this is useful if you notice that one of your sides has 2 terms, and especially if those 2 terms are fractions for both of them, and the other one just has a single term. Well, that means somehow we've added these fractions together, right? Somehow they got added together. How do you add fractions together? Well, you get a common denominator. So it seems like a good idea to get a common denominator over here. So let's do that. So here I have 1 over sine squared theta. Give myself some space. 1 over cos squared theta. So if you're not sure what your common denominator should be, then it probably should be just the 2 denominators multiplied by each other. And that's the case here. This is like if I'm adding sort of 1 over 2 plus 1 over 3, my common denominator would be 6, or 2 times 3, right? So here my common denominator is going to be sine squared theta times cos squared theta. So I'll put here a cos squared theta on the bottom. Now I can't just do something to the bottom, I have to do that to the top too. So there needs to be a cos squared theta on top. And then I'm going to make this the same denominator, so it's going to be cos squared times sine squared. So I put a sine squared theta on the bottom, but I got to do that to the top as well, so there's a sine squared on the top. All right, so that makes this first fraction cos squared theta divided by sine squared theta cos squared theta, and the second fraction is sine squared theta divided by cos squared sine squared. Well, that's the same as just sine squared theta times cos squared theta. So my denominator is the same now, so I can actually add those 2 together. So on the top, I'm going to have cos squared theta plus sine squared theta. On the bottom, I have sine squared theta cos squared theta. All right, so the good news is that I've made this a single fraction, which makes it closer to the right side, but it still doesn't look like the right side. So what are we missing? Well, what we should notice here is actually the Pythagorean identity is hiding in here. So the Pythagorean identity is that 1 is equal to cos squared theta plus sine squared theta. So this entire top here is actually just equal to 1. That means I can simplify my left side to 1 divided by sine squared theta times cos squared theta. And that actually is exactly the right side already, so you don't have to do any work to the right side at all in this case. I can say right away the left side equals the right side, my little box, and I'm done. We got there. All right, let's try one more. This one's also going to be a common denominator, but it's not necessarily obvious right away, and it involves your reciprocal trig functions too. So first thing you want to do, of course, is separate your left side and your right side. So your left side is tan squared theta plus 1. Right side is secant squared theta. And draw a line down there. Let's look at the left side because it looks a little more complicated, right? So we'll start kind of there. If I see a tan squared theta, that always makes me think quotient identity here. So that seems like a good idea to replace the tan with a sine over a cos. Now in this case, it's not just a tan theta, it's a tan squared. So that means I'm going to replace tan squared with sine squared theta over cos squared theta. And then I'm adding 1 to that whole thing. Now I can notice, well, I've got 2 different terms here, and I just have 1 term on this side. So probably it's a good idea to try the common denominator thing. Might work, might not work, but let's give it a try. So here the denominator is cos squared theta, and here the denominator is just 1. So how am I going to get a denominator that's the same? Well, my common denominator should probably be cos squared theta. So to do a common denominator, I'm going to take the 1 here and multiply by cos squared theta on the top and cos squared theta on the bottom. And now I have this common denominator of cos squared theta for both. So if I add these together, I have cos squared theta as my denominator, my common denominator. And on the top here, I had a sine squared theta. And on the top here, I have a cos squared theta. I should notice now, ooh, sine squared plus a cos squared, that looks a lot like the Pythagorean identity, which is 1 is equal to sine squared theta plus cos squared theta. So let's toss that in. Sine squared theta plus cos squared theta equals 1. So I get 1 over cos squared theta here. All right, let's take a look at the right side. This side is much simpler to simplify. The definition of secant is 1 over cos. And so the definition of secant squared theta is 1 over cos squared theta. And so we're there. The right side and the left side are equal to each other. So I can say left side equals right side. And we've made it to the end. By the way, showing these steps is actually your work here. Like that actually is the proof. So there might be a temptation to be like, oh, the right side simplifies to 1 over cos squared theta, so the left side must too, without like showing these steps in here. But those steps in here actually are the proof. Like the idea of a proof is to show how you get from here to here. If you sort of just said tan squared theta plus 1 equals 1 over cos squared theta, no one would believe you. The whole point is to show how do you get from tan squared theta plus 1 down to 1 over cos squared theta. So this is a case where showing your steps, if you don't show your steps, you really haven't actually done the proof at all. It's not sort of a matter of showing your steps just because I like to see them, but actually because that is the proof. So make sure you're showing your work really, really clearly on these proofs. All right, that is our first set of proofs. So give the ones in your practice worksheet a try. And tomorrow we'll do some even more interesting ones.